Okay, folks, this is the problem that we did in class today. And just kind of run through how to do this again. Some of you might have this already down, but just want to walk you through it again if you're studying it tonight or tomorrow and had some problems. So this problem, we want to write our rate law. Anytime you see rate law, think rate, let me shrink this down a little bit, is equal to K times my concentration of one of my reactants raised to some power times my concentration of one of the other reactants raised to another power, raised to, if there's more reactants, to another power. We don't use O because it looks too much like a zero. And then this would go on and on until we ran out of reactants. In this case, the one from class, we had 3 reactants, so we'll just stop it at here. So ultimately, the rate law, we're going to have K filled in, and we're going to have the M, N, and P filled in as well. So our idea behind trying to figure out how changing the concentration of one of these reactants affects my rate is, well, just like in any good scientific experiment, we want to maintain all variables to be the same with the exception of the one that we're trying to tweak here. So if I want to look at how the concentration of A changed things, I would try to find 2 experiments in which only the concentration of A changed. And it looks like if we look at experiment 1 and 2, in experiment 1, A is 1.25 times 10 to the negative third, and in experiment 2, A is some different number. But in experiment, or for substances B and C, those are the same. It's not necessarily important that they're the same as each other. It's just a coincidence in this problem, but they have to be the same concentration for B from trial 1 and 2, and the same concentration for C in trials 1 and 2. Alright, so that means any change that we make to the concentration of A between trials 1 and 2 is going to be what's responsible for this change in rate between experiments 1 and 2. So we're going to come up with a couple of ratios, and we're going to use run 2 over run 1. So I'm going to look at my concentrations first. 2.50 times 10 to the negative third, big M, over 1.25 times 10 to the negative third, big M. And this turns out that that's going to be 2, which means the concentration of A is doubled between trials 1 and 2. Well, let's see what effect that had on my rate. So I'm going to use my rate from trial 2 over my rate from trial 1. And this is going to be 0.0174 over 0.0087, and that's big M over S, big over M over S. I don't really care too much about units for these problems because they're just going to cancel out in the first parts here. So this actually would give me 2 as well. So I know whatever I do to my concentration, if I raise that to some power, in this case M, I'm going to see that happen in some power to my concentration, meaning if I doubled my concentration, that's what I did here, I'm either going to double my reaction rate or keep my reaction rate the same, or quadruple my reaction rate, or raise it to the 9th, or some number there. So the way I figure that out is I take the number from my reaction rate, I take the number from my concentration, what happened to my concentration, my ratio of concentration from run 2 versus 1, and I compare that to my rate 2 over rate 1. So 2 raised to what power will give you 2? Well, in this case, we don't really need to bust out the calculator. We can see that 2 raised to the first power will give me my order with respect to A. Meaning that in this reaction, if I double my concentration of A, I'm going to see a corresponding doubling of my rate, assuming the concentrations of B and C stay the same. So I only have about another 30 seconds on this screencast, so I'm going to stop it right here, and we'll pick up on the next one trying to do this for the rest of them for B and C.